Hello, physical geology students. I just wanted to follow up on the Muddiest point questions that you all submitted at the end of lecture. There were only a handful of them, so this shouldn't take too long. But there was one question about, are there any areas closer with angular unconformities, like at Sicker Point, layers folded from different time periods? So the way I'm interpreting this question is that the student wants to go and actually look at an angular unconformity themselves. And yes, there are some other possibilities closer than Sicker Point. So Sicker Point's pretty great, but let me show you some other examples of unconformities that I've seen. Remember, there are three major kinds of unconformities: disconformities, angular unconformities, and nonconformities. And let me show you some examples of each. Here's an example of a disconformity. This is in California. And basically what you're looking at here at the bottom are Miocene age layers that are around 15 million years old. And then on top of them are Pleistocene layers that are around 2 million years old. And so in between them, that sort of orange surface in the middle is the unconformity surface, basically an old soil horizon. That's why it's a different color. Here's an example of a disconformity from Ireland. This is from Northern Ireland, and you can see white-colored chalk deposits there, and then basalt, a volcanic rock, lies on top of the chalk. You can see the basalt has actually filled in low-lying areas of the landscape, ancient valleys, paleo valleys. So there's a thicker deposit of basalt filling those valleys and a thinner deposit on top of the hills. Another example of a disconformity from Ireland is on top of those basalts, soil horizon developed. The soil developed on top of the basalt, so the iron was oxidized. It was a bright orange tropical soil called a laterite, and then more basalt erupted on top of that. So you've got basically two different basalt packages separated by this ancient tropical soil horizon. Here's an example from the United States. This is up near Catskill, New York. This is an angular unconformity where basically you've got Ordovician age beds that are vertical, and then they were eroded off, and then Silurian age beds were deposited on top of those, and then they were tilted. So this is just about exactly like Sicker Point in terms of the geological setup, except this is here in America. And then finally, an example of a nonconformity. This is in the Grand Canyon, where you have 1.7 billion year old rocks overlain by Cambrian age rocks, 550 million years old. And right there on the picture on the right, you can see I'm putting my finger exactly on the unconformity surface. So right there in the space occupied by my fingernail is a missing 1.2 billion years of geologic time. That's how profound these unconformities are. One final example here, it's even more time missing. This is in Wind River Canyon, Wyoming. You see granite and schist down below, 2.9 billion years old, overlain by Cambrian age sandstone, again about 500 million years old. So if you do the math there, 2.4 billion years are missing along that horizon. All right, another question that a student asked was oil exploration. Do you have to match fossil rocks with exploration? Using correlation, using index fossils to match up strata is important for the oil exploration game, as well as for many other geologic resource industries. One person asked for clarification on the parent-daughter half-life relationship. So again, parent is the name that we give to the unstable radioactive isotope that falls apart over time. Daughter is the name that we give to the stable isotope that results from that breakdown. So you start off with a parent isotope like uranium, and then that falls apart over time. It radioactively decays, and you're left with a stable daughter product, which is lead. The half-life is the amount of time it takes for half of the parent to decay into daughter. All right, so no matter how much parent you have there, the half-life is how much time it takes for half of that parent to go away. And remarkably enough, this seems to be a fairly constant thing over geologic time. The last question that I got is, why are there only 5 isotope systems? There are more than 5 isotope systems. There are plenty of different radioactive elements, but the point here is that only 5 of them are geologically useful, which means that they have a long enough half-life that they're useful for dating, rocks, which generally are pretty old. And also that they have that particular chemistry that they fit into certain mineral crystals, but their daughter products don't fit into the mineral crystals. So those three things are basically criteria that we need for an isotope system to be useful to geologists. And if the half-life is too short, then it's not going to be useful to us, like carbon-14. If the mineral crystals will let the parents come and go, or the daughter products come and go, then that's not going to be useful either. So we need to be very choosy about the tools we use for figuring out how old rocks are, and they have to meet those three criteria. And there are only 5 isotope systems that meet those 3 criteria. So that's why there's only 5 for geology. Okay, thanks a lot. That's all the questions I had. So those are all the answers I'm going to give you. Have a good day, and I'll see you tomorrow in class. Bye.